I was an intern at Chapel for 2 years from summer of 2023 and 24. And the first, well, I'll get into it. So you all know what Chapel is. Obviously, you're here. PyTorch is it's a machine learning library in Python. It's very popular. You must have heard of it. So Chapel, my first initial internship project was to basically see, excuse me, how amenable Chapel is to machine learning style computations. And the my first project was to basically train some neural networks in pure Chapel, and to follow some um, Python tutorials and replicate that in Chapel. And I developed a very like primitive machine learning library, excuse me, in Chapel, but it really wasn't very. It was sort of like just a bunch of layers that you could compose, neural network layers, and it wasn't like a tensor library, which is what TensorFlow and PyTorch are, and they're much more flexible than just having a fixed collection of or a bunch of layers that you can just string together. They're much more powerful than that because you can develop your own sorts of ML computations and then create your own architectures of neural networks. So, excuse me. In 2024, so the year in between the two internships, I basically tried to study as much of PyTorch as I could and understand like how an ML library that's where their core data type is tensors, and that's the whole point of the library is just manipulating tensors, and how a library like that worked. And so once the internship started, I just my goal was, can we make this in Chapel? And the answer is yes. It's pretty tricky, but so what sort of the things that this library should have is first, like I think the most important thing is having a familiar syntax or just like a familiar style. So pretty similar to like PyTorch or TensorFlow. So any sort of skills you have in these other existing libraries can easily transfer over into this Chapel library. So you can like very quickly replicate your code and just have the same sort of feature set that you're used to. Um, and you should like if you have data or existing models that are already trained in using one library, there should be um, tools in the Chapel side that are really easy to just pull it in and utilize what you already have with minimal work. So that would make the barrier to entry for Chapel very low. Um, the other thing, it should be GPU enabled. So Chapel, in the 2024 internship, Chapel was really like, I guess like doing a lot of development on their GPU stuff, and it was getting really good. So I wanted that to be a core focus. And the use case, for this is obviously like, you're a data scientist and let me mute. Um, so like you're a data scientist and you train a neural network using PyTorch, and you should just be able to like instantly run that in Chapel with like minimal effort. Um, so the result of my internship was I developed a machine learning library, and we named it ChAI for Chapel AI. And it has like it's structured in a way that you can like either there's many entry points for a user. So you can either be like super high level and just use existing tools and string together tensor operations, or you can go at the very low level and write your own kernels in Chapel and register those into the entire system and then have those accessible to you at a high level too. There's also like some predefined layer types and things like that. So you can have like convolution layers and linear layers, softmax, things like that. Something that it should also be able to do is a distributed inference, and we did sort of have that. It was sort of you kind of had to do it manually. It wasn't very automatic, but if I had more time, then there would be more support for that. And um, there was some functionality for um, turning a PyTorch model into a chapel model. And this was there was like a conversion thing for that. So the architecture of this first system was it's pretty tricky to write like a general tensor system in Chapel. The main reason is the it turned out to be the compile time rank, um, or sorry, the dimensionality of arrays that needs to be known at compile time made it really tricky from a usability standpoint. So libraries like TensorFlow and PyTorch, the dimensionality of tensors is or arrays is known at runtime, and that can change. So there is no like typing restriction for that. But in order to make these systems look or this system look familiar, we needed to get rid of that. So there we kind of had this several layers of like indirection or whatever. So at the base, you have this like record wrapped array. This is like an ND array. This is the most primitive. Um, it's basically a chapel array just wrapped as a record. And then there's a bunch of like methods on that data type that gives you things like you can do like the convolve operation or matrix multiplication, things like that. And so above that, there's a like a device controller for these these arrays. And this device controller level basically allows you to do that. In PyTorch, you can say, well, I have this sensor, and then I want to control what device it's on. In Chapel, you have this construct, the on construct, which you can say, I want to run this code on a particular locale, but you don't really have control over, like, let's say you're on locale 0, and you want to just move the data and just have it there and save it for later on locale 1. There isn't really a way to do that. There's a way you can do that kind of in the lower level of lower at one of like the primitive language constructs where you have like I think it's called remote variables, but that's basically what this is. It just allows you to say, well, I have a piece of data and I can put it on a particular locale. And then the next layers or the next level is this autograd system. So this controls like, or it keeps track of what operations you do and how you compose them. So you have this, you have the capability to do automatic differentiation on your tensors. And the reason that this is sort of grayed out is because it's quite tricky to represent this for each operation. Each operation has, it's a function, and then it also has a corresponding derivative with respect to each input. So writing those is very tricky, and making sure that those operations are performant is hard. So for the interest of time, we sort of left those out and then just short circuited them so they don't actually have support for automatic differentiation. But that's not really the point. The point sort of shifted to be more sort of inference rather than training. Like you can do the training in PyTorch and then just do the load it into Chapel and then do inference on the Chapel set. So another main entry point for the user is this static rank tensor thing. And what this does is it's a wrap, it's an interface that preserves the dimensionality information at compile time and allows you to treat, this very rich tensor data structure as a basic chapel array. And that's very useful. You can use the for all loops with this because they require rank information. The other entry point that you'd probably use the most is the unranked thing. So once you have this kind of data structure, it's basically like a PyTorch array. And for this, you can't index into it. You can't, say like square brackets, 0, 0, and then have like a real number value, because there is no rank information. And from here, this is how you sort of string together all of your operations and build up your neural network computations. And then from there, you have your PyTorch-like support, and then you can load models in via PyTorch, and you basically deal with these two systems the most. You can do this, or you can pick any combination you like, but this is like the most common entry points that you would use, at least if you're not like a hardcore Chapel person. No. So what we found is that a lot of these operations, if you write them in pure Chapel, like if you write the GPU kernels in pure Chapel, they are not as fast as PyTorch. Um, they're usually about like 2 to 3 orders of magnitude slower. And this is just because, PyTorch has had so much like development and really like really smart numerical methods people working on these like low level kernels. So they're just they're much better optimized than the GPU code that Chapel generates for these. So um, over the next year, from like the summer of 2024 till now, I've been working on with a team of some other undergrads as a capstone project. We were trying to integrate libtorch, which is the C++ backend for PyTorch, into into ChAI. So ChAI can either target pure Chapel code or libtorch code. And so you would do this for like really expensive operations. An example is like the 2D convolution operation, which PyTorch's version is just so much faster. And also you don't need, once you have this sort of structure, you don't need to re-implement any sort of operation that you want to use in ChAI if it doesn't have one, or in Chapel. You could just pull in whatever operation PyTorch has. So it's from a time perspective, this is a much better strategy. And it also makes it easier to load like very native PyTorch file formats like PTH and PT. I think PT is the newer one. Um, and you can also load PyTorch models as black boxes. So you don't even need to represent the neural network in Chapel. You can do everything else in Chapel and do your like um, um, your distribution scheme and whatever in Chapel, and then just have like calling PyTorch directly without the Python layer. So it's very, very fast in that sense. So this graphic sort of illustrates that. So PyTorch is just basically a Python wrapper, offers like it's like a metadata wrapper for these low-level C++ calls, and ChAI does the same thing. So it can either reference, C++ libtorch code, or that you write and you wrap with Chapel, or you can use uh, your own Chapel kernels that you write. So you can sort of mix and match. Um, and these are the different ways you can use ChAI. So you can either like I said, um, write your own Chapel kernel or use a PyTorch implementation. It'll probably be faster, but it might not be if depending on what the computation is. Um, and so, it'll take less time if you just treat like your whatever model you want to use, you write it in PyTorch and you just compile it to a PT file and then pull it into ChAI. Or you can mix and match. So you can do like parts of your neural network architecture can be like the expensive parts, maybe like a multi-head attention can be for or can be done in PyTorch, and you just use that in or you pull that into ChAI, or you can do everything in Chapel and represent your entire ChAI neural network as Chapel code. Um, so these are some examples. So initially, at the end of the summer, I had a working MNIST model digit classification, which is MNIST is a data set where you have like handwritten digits and you map them to their numeric representation. Or resonant, I think Shreyas and Engin developed this, or Jade too. And this was really cool. This, can take basically any image, usually of like animals or like broccoli, and tell you what it is. And then in the last year, we developed some pretty cool examples. Like one is a style transfer, which takes like, you know, an image feed, and then it gives you like that image in the style of Vincent van Gogh's Starry Night, or in this like I forget what painting this is, but it's like a mosaic painting. Um, or you can do like a very just primitive operation, like a Sobel image convolution or an edge detection operation. So I'll actually show you this right now. It might take a few seconds. Um, oh, here it is. Yeah. So this is me in Starry Night, and this is running. This is using Chapel. So it's libtorch, and then it's Chapel exported as a C library called from a C program that does the OpenGL and image feed thing. So yeah. Um, And last, I want to thank I did this before in my internship presentation, but I wanted to thank Michelle and Engin. Michelle was sort of like a high-level director for my project. Engin helped me a lot with these like low-level operations or operation optimization. And Jay, Daniel, and Brandon were great mentors, and they helped me throughout the process and all the engineering problems. They really worked with me. So um, thank you very much. Yeah, I really like the Chapel team, and I'm very excited to present this. I've been looking forward to presenting this for a while. So, are there any questions?